I think I was muted. So, hi everyone. I welcome you all to the live problem solving session on multiphase flow. That is sixth session, and I will be going to discuss a few questions that will be going to help you in the exam. And so, let's start with the questions. Okay. So, first question is this. 1 minute. So, first question is a packed bed is composed of cylinders, cylindrical particle or cylinders having a diameter d is equals to 0.02 meter and length h, that is height of the pipe bed, is equal to the diameter, that is d. The bulk density of overall packed bed is 962 kg per meter cube, and the density of the solid cylinder is 1600 kg per meter cube. So we find A, calculate the void fraction. And calculate effective diameter of particle. Okay. So these two things need to calculate. So take some time and try to solve it, and then we'll see the solution. Okay. Okay, so let's look at the solution. So here we have total mass of bed. So bulk density of overall packed bed is 962 kg per meter cube. So that it means that if we take 1 meter cube of bed, then it has 962 kg of cylindrical or cylinders. Okay. And this mass, and we know the volume of cylinder is. So we want to calculate the volume of the cylinder is 962 divided by the density of the cylinder, that is 1600 kg per meter cube. And so volume of cylinder we got is 0.601. So epsilon void fraction is nothing but the volume of voids in the bed divided by total volume. And we have taken total volume to be 1 meter cube. So epsilon is 1 minus volume of voids is 1 minus of the volume of the packing, that is 0.601 divided by 1, and that comes out to be 0.399. Okay, I hope it is clear. Then we need to calculate. So this is the solution to the first part. Then in the second part, we need to calculate the effective particle diameter. So effective particle diameter is nothing but the formula for effective particle diameter is 6 by a specific surface area. And specific surface area we know that is nothing but the surface area of particle divided by the volume of the particle. And for this case, surface area of particle is nothing but pi. So we have a cylinder. So net surface area is surface area of this, surface area of this, and surface area. So net surface area is 2 into pi d square by 4, that is of this face, plus pi d square by 4 into this is pi d by 2 into uh, length of this cylinder, and so this is height of the cylinder. This is given to be h. We know h is d, so this is nothing but pi d by 2 into h, sorry, pi dh, because it's diameter. Okay, so we know substitute h to be d. So it comes out to be pi d square by 2 plus pi d square, and that is 3 by 2 pi d square. And what is the volume of the particle? Volume of the particle is pi uh, d square by 4 into h. Okay, so that is pi d square into d by 4. That comes out to be pi d cube by 4. So a specific surface area of the particles comes out to be 3 by 2 pi d square divided by pi d cube by 4. And so it is nothing but d by 4 pi by rho not d by 4. I think it should be 2, it should be 6 by d. And so effective particle diameter is 6 by av and 6 by d. So this is d. So that is 0.02 meter. That is the answer for part 2. Okay. Now let's move on to the questions regarding the fluidized bed. So we have a question. On fluidized bed. So we are having a solid particle having a size of 0.12 mm, a shape factor of ys to be 0.88, and density of 1000 kg per meter cube are to be fluidized using air at 280 atmospheric pressure and 25 degrees centigrade. The voidage at minimum fluidizing condition is 0.42. Find first if the cross-sectional area of the empty bed is 0.3 meter square and bed contains 300 kg of solid. Calculate the minimum height of fluidized bed. Then we have another question, another part to this. Calculate pressure drop at minimum fluidized condition. Okay, so try this question. I will be waiting for a few minutes and then we'll see. Okay, so the first question is on if the cross-section area of the empty bed is this and bed contains 300 kg of solid, calculate the minimum height of the fluidized bed. So we need to calculate the height of the fluidized bed. So because of the fluidization, there will be a change in the height of the bed, and that height we need to calculate. And how we can calculate is that basically we need to equalize the volume, total volume of the particles. So so the total volume should be equal, and total volume is nothing but, let's say, if we have in a very simple terms, if we have a bed with porosity epsilon 1 and the area should be same and has height L, height of the fluid bed is L1, then in order to equate the volume, and another bed having bed or having same volume has having porosity 2 epsilon 2, area of the cross-sectional area should be same, and length is the height of the fluidized bed. And so if we wanted to equalize both of them, so it is nothing but A into L1 into 1 minus epsilon 1. This should be equals to A into L2 into 1 minus epsilon 2. Okay. So L1 by L2 should be equals to 1 minus epsilon 2 divided by 1 minus epsilon 1. So this is the formula to calculate the height of the fluidized bed when you have two different kind of porosity. Basically, uh, here we need to calculate the cross. Here we will be having a cross-sectional area of the empty bed. So here we will be going to comparing the minimum fluidized condition with the empty bed. Okay, so we have epsilon MF, that is at minimum fluidized condition, the porosity is 0.42, and for the case of the voidage at the minimum fluidizing condition is 0.42, and we need to calculate the height of the bed at minimum fluidized condition. Okay. So, hi Dinesh, are you there?
Hi. Just
Hi.
joined.
Yeah. So, uh, I am just discussing the questions. So that is going on record. So that's why maybe someone will look and see.
No
So
worries. Yeah. Please go ahead.
yeah. So basically, this question now I'm discussing is regarding the minimum fluidized bed. I don't know if you, because you are from aerospace, I don't know if you heard all those terms or not.
It's okay. It's okay. I mean,
Okay.
it's fine. I get an idea. You're doing continuity equation here.
Yeah, we are looking at the fluidized bed. So we are having this air fluid in the packed bed. Let's say we are having a packed bed with, so we are
Okay.
having length. So if it has porosity epsilon 1, it has length L1. And so I'm discussing the two, how to compare both. So we need,
Okay.
there is a, so there is a condition came, so basically minimum fluidized condition is the condition where the molecules, the particles are suspended in the gas, and in that condition we need to calculate the length of that height, or the height of that bed where particles are particle are suspended in a way that the gravity, the net pressure drop is just equal to the gravity that is there. So gravity minus drag, sorry, gravity minus buoyancy force is should be the net pressure drop across the particle. So that is there. And so that is the condition for minimum fluidized bed condition. And so we need to calculate the minimum height of the fluidized bed. Okay. So uh, L of MF, let's say, into 1 minus epsilon MF, it should be equals to the another length, let's say L1 and 1 minus epsilon 1. So I need to calculate L of MF. I know epsilon of MF. And another condition I am having is that, so we have an empty bed. So empty bed means it is the value of, so basically epsilon 1 minus epsilon 1 is nothing but, because it's empty bed, so it is all the particles over there. So the volume of the particles divided by the total volume. And so that is, so we have 300 kg of solid divided by 1, that is the volume of the solid, sorry, density of the solid. And so what we get is to be 0.3. Okay. So, and length of the, so first we need to calculate also the length of the empty bed. So L1 into A should be equals to, that is given. So we have calculated that is to be, so this is the volume of the particles, and this is 0.3. So L1 into area is given, and area of the empty bed is 0.3. 0.3, and it should be equals to 0.3. So L1 comes out to be 1. Okay. So it is actually the volume of the particles. Okay. So because the bed is empty, so there is this term should be 1, and so L of MF comes out to be 1. L1 is 1 divided by 1 minus epsilon of MF, and that is 1 minus 0.42, and that is 1 by divided by 0.58, and so it is 1.72. Did you understand this? What I just talked.
I'm just following.
So basically, this is the we are just equating the volume, and so we have calculated the volume of the particle, and because the bed is empty, so epsilon is 0. So uh, we have epsilon 1 should be 0, and so we calculated the L. Okay.
Okay.
So this is this is L1. L1 we have calculated, and then by putting this, we get the minimum fluidized height of the minimum fluidized bed condition.
Okay. Please continue. I think I will follow from the next problem. This problem I just joined.
Okay, okay. 1 minute. Yeah. So second part is we need to calculate the pressure drop at the minimum fluidized condition. And so as I told, pressure drop is balanced. So pressure drop is nothing but the rho of particle minus rho of fluid into the volume of the packed bed, that is A into L at MF into 1 minus epsilon MF. Okay. So that is coming by just by the balance of the buoyancy force and the gravity force. So that is rho P minus rho F. So we need to calculate, we have rho P. Rho P we have, that is rho of the particle. That is 1000 kg per meter cube. Then we have to calculate rho fluid. So rho fluid is nothing but M by RT into P. The pressure is given. So mass, it's basically air. So we are having a air. So for air, we have a mass for 1 mole, that is around 28.97 divided by 1000 because it's in gram. R is 8.314. Temperature is 225 degrees centigrade. So that is 298 Kelvin. And pressure is given to be 2 atm. So 2 atm means 2 into 10 to the power 5 Pascal. And so on solving this, what we get is rho of fluid to be, so I've already calculated, that is 2.3 kg per meter cube. And we just need to substitute all these in that equation. So that is 1000 minus 2.3 into G. So basically A should not be there because A will cancel out. Into 9.8 into 1 minus 0.42, that is, and length of the minimum fluidized bed we have just calculated, that is 1.72. And so the net pressure drops coming out to be 0.0978, and we have 5 Pascal. I think I should check it once. I think it's correct. Yeah, pressure drop is correct. So that is this question. Okay, so let's look at next question. First, next question will be easier comparatively. Next question is, in a fluidized bed, particle diameter is 500 micrometer. Slip velocity is 2 meter per second, and void fraction is 0.75. Air viscosity is 18.6 Pascal second. Air density is 1.18 kg per meter cube. Void fraction at minimum fluidized bed is 0.4. So we need to calculate first Reynolds number. Second, calculate the drag coefficient using Gidaspa drag correlation. Okay. So I think Dinesh, this is the easy question. Maybe you are able to follow it. It's a straightforward.
Yeah. So how would you compare? So you consider the Reynolds number of depending on the particle diameter, is it?
Yeah, it's a particle Reynolds number.
So it's like rho v d by mu. How can we know the v actually? Like the maximum velocity.
Slip velocity is given, right?
Okay. Yeah, so it's pretty straightforward. Okay. So this viscosity, dynamics viscosity, no, if I'm not wrong.
What?
The viscosity, air viscosity.
Yeah.
It is the dynamic viscosity, right? You know what I mean? Yeah, it is dynamic. I think it's dynamic.
Yeah,
Yeah.
fluid. No, it's a dynamic viscosity. Yeah,
Yeah.
micropascals.
So I
Yeah.
should do rho is 1.18. Velocity is 2. D is 500. Acha, both are micro. Those gets cancelled, no?
Yeah.
That's interesting. So 500 by 18.6. Uh, okay, so we have 10. So 1.18 by 1.86 into 10 square. How much is that? Let me check. Calculate 1.86. 63 Reynolds number.
Yeah, so there is a catch here.
Okay. She's
So because void fraction is there,
oh, so the density changes.
yeah, so we need to calculate if we are calculating the particle Reynolds number, then it should be 1 minus of void
Correct.
fraction.
I think I should do so wide fraction matlab it is 0.75. So the density will be 0.75 of 1.18, no?
No, it should be like if you are calculating particles Reynolds number, then it should be 1 minus void fraction.
Minus. Okay.
And if it is you are calculating fluids Reynolds number, then it is like as it is epsilon into
So multiplied by 0.25. How much is that? 0.25. 15.8. Is it the right answer?
1 minute. 47. Yeah, 15.8, right?
Yeah, that's right.
What is the what is the fluids Reynolds number?
It depends on the diameter of the fluidized bed, no? Am I right? Is that right? Is that right way to think?
No, I think yeah, 1 minute.
What does fluid Reynolds number होता क्या वहाँ पे? Can you check?
No, if it's the particle Reynolds number, right?
Yeah.
Reynolds number of particle is rho f, velocity of fluid. So velocity of the particle, so slip velocity of the particle, that is u minus v into diameter of the particle and void fraction.
Or should we do 0.75? Do you think that gives us the Reynolds number of the fluid rather than doing 0.25 multiplied by?
Yeah, that will be the case, right? Into epsilon. So this is if I'm putting, so this is for the fluid. So void fraction is there. So for fluid, so what we need to calculate fluid and void fraction is there. So that is epsilon. And this is mu. For case of particle, it is rho f slip velocity. I think I should take magnitude into dp into 1 minus epsilon. Right? Do you think it's correct or not?
The particle का तो we got it right. Right?
Yeah, yeah.
Yeah. So I think it's just that 1 minus ka. That's what I have said as well. I mean, if I do a thing is right, I don't know how it is defined. So I mean, it's all
Oh,
definition,
okay,
no?
okay. Yeah, I will be. Yeah, 1 minute. I will check. They have did. They did. Hmm. Okay. So, so rho v is epsilon v. Particle Reynolds number is defined here is like Re P epsilon into rho epsilon into rho u minus v divided by
Okay. So density diameter of the particle कहाँ पे गया? हाँ वही ना. We wrote the same thing, no? No, we took 1 minus. That's what. So particle is like, I think you should
actually
consider the
there
fluid
is
surrounding.
1 minus epsilon is coming. I was concerned about that.
Oh, okay. Maybe the density is also like that. No, it's not. Is that what it is?
Uh, yeah, density is also there now, so that's why I think it's coming. The particle Reynolds number is defined as 1 minus epsilon into mu g prime is 25 divided by the rate of 0.50 per second divided by 0.0. Yeah, I got completely confused in this.
It's all right.
So I don't know which Reynolds number they are exactly asking. Might if we are calculating the answer that we are getting in terms of Reynolds number, I think they have just asked calculate Reynolds number. Calculate Reynolds number of what? Calculate Reynolds number is okay, but actually answer that is coming. So for this, the answer is coming out to be uh, it is coming out to be 47.58. The correct answer is 47.58. We need to figure it out like, which Reynolds number they are asking. Most probably they are asking the Reynolds number of fluid because uh, rho mu minus v into epsilon, that's the void fraction of fluid. That's the void fraction into divided by mu. This is particle length. So rho f is Uh, yeah, you have calculated now, right?
You
You have calculated this, right?
yes. First I calculate that.
What is
So I got that 66.
no, not 66. It's epsilon is in the multiplier. So epsilon because void fraction is there because that is the amount of gas that is there, like 0.75 of the total volume. Air is just the total. This so the velocity of air is also like that,
Okay.
right? Hello, Dinesh.
So
Did you
epsilon is what I computed in the first, no?
what you have calculated? You have calculated 60.
See, I think I got something. See, I got 1.18 into
It's
2.
63.44. You have calculated something like this into it should be multiplied by 0.75. That's the void fraction. That is the
Correct,
most.
correct, 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 correct,
That
correct.
was 47.58.
Okay,
So we are assuming that it to be the Reynolds number of fluid. What now I will clarify maybe in the next session. I will
sure.
just come up with this out. I'm sorry about that, but so drag coefficient is nothing but 24 by RE because Reynolds number is uh, low, very low comparatively. Uh, Although not in the Stokes regime, but still, uh, it's the fluids in all number. So 24 by RE, and so we have so we have 24 divided by 47.58. So it is comes out to be 0.504. Okay. So I will clarify uh, a bit on Reynolds number in the next session. Yeah, let's look at the next question. If the friction vector for a single particle falling under gravity in water is 0.005, then calculate the Richardson-Zaki index. A, if RE is given to be 300. So we know that Richardson-Zaki index is nothing but K formula is this 4.45 into RE to the power minus 0.1, and so 4.45 into 300 to the power minus 0.1. So what we get is 2.515. Okay. Okay. So now let's look some questions on that was come in gate. So it's gate 2011 question. The question is this. So for a liquid liquid flowing through a packed bed. The pressure drop drop per unit length of the bed is delta P by L is equals to 150 mu F to V naught bar 1 minus epsilon square divided by P of S dP square into epsilon cube plus 1.75 rho F V naught square 1 minus epsilon divided by P of S dP into epsilon cube, where V naught is the superficial velocity, epsilon is the bed porosity, dP is the average particle size, ES is the particle sphericity, rho F is liquid density, and mu F is liquid viscosity. So diameter of the particle is given. So given data is 10 to the power minus 3 meter. Sphericity is 0.8. Rho F is 1000 kg per meter cube. Fluid viscosity is 10 to the power minus 3 kg meter inverse second inverse. Okay. Particle density is 2500 kg per meter cube and G is 9.8 meter per second square. So the question is, when V naught is 0.005 meter per second and epsilon is 0.5, which one of the following is correct value for the ratio of the viscous loss to the kinetic energy loss. So options are A 0.09, B 1.07, C 10.71, D 93. That is question A. Question B part is on further increasing V naught, incipient fluidization is achieved. Assuming that the porosity of the bed remains unaltered. The pressure drop per unit length under incipient fluidization condition is 3675 7350 14700 73501. Okay, so try to understand this question. You have take some time and then we'll solve this question. So let's solve the question. So basically, in first question, let's read it. Part A. So when V naught is 0.05 meter per second and epsilon is 0.5, which one of the following is correct value for the ratio of viscous loss to the kinetic energy loss? So what is the viscous loss and what is the kinetic energy loss? So basically, we are looking, so it is about the pressure drop due to the viscous loss and pressure drop due to the kinetic energy loss. So if you see, this is nothing but the kinetic energy loss. It is just, you can see directly half of V square, that is kinetic energy loss. And we are having viscosity here, so viscous dissipation, so that is viscous loss. and we need to take the ratio of these two. So if we took the ratio of these two, so that come out to be viscous loss divided by kinetic energy loss. It should be come out to be 150 divided by 1.75 into mu by rho 1 minus epsilon divided by Ps into dP into V naught. Wow. Okay, so we need to calculate this and we'll get 150 by 1.75. It is coming from, it is just by taking the ratio of these two. So 150 divided by 1.75 upon, so V naught in the denominator comes because it's V square, and 1 minus epsilon come in the denominator because it's square here. Epsilon cube cancel out each other. Epsilon Cs dP comes in the uh, denominator because it is there in the denominator, and so we will just calculate it. So mu we know, so that is there 10 to the minus 3 divided by 1000. Epsilon is given 0.5, so that is 0.5. Sphericity phi, yes, that is given 0.8. It's just the formula based question, but you have to, and you should know what is viscous loss and what is kinetic energy loss, then only you will be able to get it. dP, particle diameter is 10 to the minus 3 meter. And velocity is 0.005. This goes, this goes 100. So what we get is 1000, 150 into 100 divided by 40 into 175, and it comes out to be 10.71. Am I missing something? 0 point is there, particle diameter is there. Uh, yeah, I missed the 0. That's why now it's correct. Okay. Now, so the correct option is this. Let's look at the B part. So at incipient fluidization, it is just another word for the minimum fluidized condition. Fluidization. We've already calculated. So here we have already calculated it. It is equivalent to the minimum fluidized condition, and so we know it is just the pressure, delta P we need to calculate. So delta P comes out to be length G rho P minus rho F into 1 minus epsilon. So what we have to calculate? We need to calculate pressure drop per unit length. So delta P by So G is 9.8 into 500 minus 1000 into 0.5, and it comes out to be 7350 Pascal. The correct option is this. So I think I have covered most of the questions that will be going to help you in the exam or in the some of the assignments. So we have discussed around uh, 4, 6, around 10 questions, and so 10 or 12 questions. So I think that will be helpful for you. If you have any doubt, you can always reach me to shyam20@itk.sm. I think all of these are the important questions, and so let's wrap up the session. Okay, thank you. Thank you. Bye.